Okay. Yeah, hi. It's great honor to present my research to you or guys. And I'm Junbom Kwon, and I'm a research scientist at Seoul National University. So I will be introducing Swift, our deep learning application for functional MRIs. This research has been accepted at URIS 2023, and you can find preprints and codes in the slides. Yeah, so free to ask questions during presentation. Yeah, so firstly, I will introduce our vision for foundation model. So foundation model is an adaptable framework that can be applied to multiple tasks. So by pre-training the model with a large scale data set even once, foundation model can be applied to various downstream tasks via transfer learning. So this approach is useful when acquiring the label is very hard, but there are a lot of data sets without labels. Ever since large language models such as ChatGPT has emerged, foundation models for vision, NLP tasks, climate, and in the medical domain have been developed to solve multiple research questions. Yeah. The objective of our project is to develop a foundation model for brain dynamics, which we call NeuroAI. So to apply machine learning or deep learning models to fMRI data, we have to collect large numbers of fMRI scans to solve our specific research questions. However, it is almost impossible for individual researchers to collect thousands of samples to deal with their own research questions. If we can develop a foundation model for brain imaging, we can transfer knowledge from large-scale open-source data sets for solving various research questions in neuroscience. Yeah, so let me introduce, let me briefly explain the fMRI data. So fMRI consists of sequences of volumes. So it is a high dimensional data with low signal to noise ratio. So to increase the signal to noise ratio, previous research in neuroscience has reduced the dimension of fMRI using predetermined brain templates. However, depending on the type of brain templates, the performance differs a lot. For example, if we use fMRI from children, we have to use unique templates for the children, but other brain template is required for adults. In addition, feature extraction inevitably causes the loss of subtle individual difference. Therefore, we expect that deep learning application can extract rich representation from minimally preprocessed fMRI datasets. Yeah. However, there were three challenges in training a foundation model for fMRI dataset. Firstly, we had to prepare at least 120 terabytes of storage to load hundreds of thousands of fMRI scans. In addition, it required a lot of GPU resources, since our model size should be large enough to train with these amount of fMRI datasets. These two requirements were satisfied by the support of NERSC. The last requirement was to develop efficient and scalable model architecture that exhibits high predictive performances. Also, the predictive performance should consistently increase as the model and data size increases. This is why we have developed transformer architecture for fMRI, Swift. Yeah, so our model Swift is based on Swin transformers, which reduces the computational complexity of transformers by applying local window attention. These local windows are shifted after each layer to allow communication between distant tokens. In this context, maybe the specific region of the brain. Swin transformers also attain a hierarchical structure by merging neighboring patches into a bigger patch, similar to how CNNs have a hierarchical structure through the pooling layers. So to process 4D fMRI data, we have expanded core Swin transformer architecture to be 4-dimensional. We also have introduced some additional optimizations, such as absolute position embedding or global attention layer for the last stage. Through this, we have made the use of transformers extremely efficient in terms of memory and computations in fMRI processing. So this is our architecture of Swift. The model accepts fMRI images divide and embed the volumes and runs them through the transformer encoder. Then we carry out various tasks using the extracted features. We evaluated shift on 3 kinds of data sets by predicting sex, age, and intelligence scores. So, as a baseline model, BNT is the previous state-of-art ROI-based deep learning model, and TFF is a conventional for the fMRI transformers. Swift worked better compared to baseline models in general. In sex classification, Swift reached almost 100% accuracy scores in HCP and UK Biobank datasets. In age regression tasks, Swift showed decreased mean absolute errors by 21% in HCP dataset and 34% in UK Biobank dataset compared to BNT model. In intelligence prediction tasks, Swift showed a small gain in mean absolute error, but it is impressive considering that intelligence prediction is a very challenging task in general. Furthermore, Swift showed scalable performance increase with more training samples. In UK Biobank sex and age prediction tasks, it showed 13% and 54% increase from 100 samples to 5,000 samples. This suggests that Swift can be trained effectively with a large number of data sets. In addition, it is notable that the model can predict these variables to some extent with only 100 samples. Using only 300 fMRI scans, Swift outperformed BNT, trained with more than 6,000 fMRI scans. Yep. And then we interpreted the sex classification research using integrated gradients. In all datasets, default mode networks known to activate at rest were explainable for the sex difference. Brain regions dependent on each dataset were also observed, and they were usually brain regions highly connected with other brain regions, such as thalamus, insular cortex, and inferior temporal gyrus. Shift is more efficient than the existing 4D fMRI transformer as well. While existing 4D fMRI transformer shows comparable performances as Swift in some cases, Swift is much more efficient. Swift requires 154 times fewer parameters and 15 times fewer operations, making it about 2 times faster. We did not include other RI-based models for fair comparison, considering the long pre-processing steps for those models. By pre-training Swift in self-supervised manner, we expected Swift to show better performance at downstream tasks. Therefore, we adapted 2 contrastive learning strategies for video representation learning. Firstly, we used instance contrast loss to make Swift better learn subtle individual difference. Secondly, we used local contrast loss to make Swift learn temporal dependencies between nearby and far away fMRI volumes. As a result, we could find Swift pre-trained with UK Biobank shows improved performance in intelligence prediction tasks of other 2 datasets. Yep. I have 1 slide left, so I will answer to the question after the next slide. Yeah, so we are now working on large-scale pre-training with bigger model size and data set. Also, Swift can be applied to many research questions that can be dealt with fMRI data, including clinical application and brain decoding tasks as well. So Swift will continue to develop as researchers worldwide tries to solve their own problem with Swift. Yeah, so we are open to any kind of collaboration. Yeah, so feel free to ask any questions and show any interest regarding our research. Yeah. So thank you for listening to our presentation, and please feel free to contact me for further information. Yeah, thank you. Yeah, and then I will. Yeah.
Thanks so much.
Yeah. Yep. So, Kalova, do you have any question?
Hey, yeah, thank you so much. So I was wondering, I know that, for example, in speech decoding, a similar paradigm of contrastive learning is oftentimes used to learn positive and negative samples coming from time series data. And very frequently for speech decoding or phoneme decoding tasks specifically, researchers seek to use large language models. But one
Yeah.
problem that tends to arise is that the previous pre-processing yields high-dimensional tensors that
Yeah.
are stored as multidimensional objects, whereas existing transformer architectures typically take one-dimensional inputs, which tend to be time series data. So
Yeah.
this in a way seems analogous to how image data is being processed in
Yeah.
Swift, given that it's inherently multidimensional.
Yeah.
So I was wondering if you can see some sort of translational application of a similar pipeline, because basically in speech processing, the existing problem in the status quo seems to lie in the convergence step from the high dimensional tensors to one
Yeah.
dimensional data that's compatible with existing large language models so
Yeah.
as to avoid lossy compression.
Yeah. Yeah. So yeah, to summarize your question, then are you asking whether um is there any issues regarding using traditional large language models in this kind of models?
Oh,
Or
more
yeah,
like
yeah,
so
yeah,
so more like more broadly and
yeah,
generally, how
yeah,
can how could the insights from this architecture be leveraged to build similar models to deal with the integration of high-dimensional tensors
yeah.
with pre-existing, pre-trained large language models that typically take
Mm,
one-dimensional inputs into their convolutional layers?
yeah, I think it's really great question. And yeah, so yeah, I think I have to think over a little bit. Uh, yeah, I haven't tried to use this Swift model for apply, yeah, maybe adapting the traditional large language models for this application because, uh, as you know, it is basically from the vision domain. So Swin Transformer is for processing the image data set. So a little bit kind of, uh, I think it's hard to directly apply the vision transformer for though maybe yeah we can use pre-trained vision transformer in this context maybe but um um it's just mm, I think I didn't catch up exact point of your questions. Sorry to yes, I'm sorry, but yeah, can you make it more
So
clear? Yeah,
okay, yeah, sure, sorry. So
yeah,
basically, a pattern I'm noticing in most transformer models across
yeah,
different modalities is that they
yeah,
typically tend to take like simpler inputs, quote unquote. And what I find very interesting about the architecture of Swift is that they inherently know how to deal with high dimensional inputs because
yeah,
that's
yeah,
the nature of image inputs. And I'm
yeah,
trying to understand a bit better the intuition and mathematical computations happening at each step with regards to how the convolutions are computed. And maybe like if you could walk us through the I guess, underlying mathematics in greater
yeah,
detail, that would be super helpful
yeah, yeah,
because I'm still not super sure about how
yeah.
the process works and how it differs from
Mm.
simpler and more established traditional transformer pipelines.
Yeah, maybe you mean in this context, maybe using CNN layers for encoding the input data set, right?
Yeah,
Yeah. So the baseline models we used, the TFF model adopts the CNN layers to embed each volumes to one dimension vector and then input those vectors to traditional transformers. So maybe those kind of architecture is more similar to the model you mentioned, I think. And we tried those model, but we found that it is hard to optimize the gap between the CNN layers and transformers. So the training was a little bit unstable, training those kind of models because yeah, CNN and transformer has different characteristics for training. So in for those cases, we pre-train the CNN layers in advance, and then we embedded fMRI, no, and then embed transformers after the pre-training steps. But yeah, so to summarize, it'll be the biggest challenges for us to stabilize the model's training with those CNN layers, using CNN layers with decreasing the dimension of the input data, high dimension input data. So we just remove those two different architectures, CNN and transformers, and just we incorporated it as a one transformer layers for Swift. Yes. So I'm not sure whether it is right answer for you.
Yeah, sounds good. Thank you.
Yeah. Okay. Yeah, so Jonathan asked a question regarding the data set. So how did it work with different sampling frequencies? Oh, yeah. So yeah, I think it's a great question as well. So as you know, depending on the data set, they have different sampling frequencies. And so we have tried changing the sampling rate of the fMRI scans by just giving some strides for fMRI data as well. And then we observed that it impacts on the performance as well. But yeah, I didn't include those results. But yeah, in this context, we did not care about the sampling frequencies a lot because we did not combine the multiple data set with one model. So it was not a big issue in this context, but I think the different sampling frequencies would be one of the biggest issues to combine the multiple data sets. Yeah. So yeah, I think it's a great research topics as well.
There's sampling frequency. There's also
Yeah.
normalization. So like if you pre-train on UK Biobank and then you fine tune on ABCD, how do you handle brains being in different spaces?
Yeah, so different spaces. Oh, yeah. In fact, indeed I didn't care much for those issues yet. Yeah, but I think it's the reason why the pre-training was showing the marginal increase in the performance. So maybe I have to consider it in the future research. Yeah, but yeah.
I mean, it's clearly able
Yeah.
to work to some degree, even though they're in different brain spaces, right?
Yeah. I think
Is that expected, or is that like you're potentially losing accuracy by doing that, but it's still good enough to beat other methods?
Yeah, maybe it is more similar to the latter approach. Yeah, so I just tried it with trial and errors, and it showed better performance. Yeah, transferring from one dataset to others. But yeah, maybe considering those kind of points would make it better, I think.
I also wanted to ask you, so this is 4D transformers. It doesn't have to be fMRI, right? You could apply it to MEG, you could apply it to any data set that's four-dimensional, presumably, right?
Yeah.
So do you have intentions for working across multimodal data sets?
Oh, yeah. I think we can apply Swift for other modality as well, and maybe we can use it for combining multiple modalities of fMRI, multiple modalities of data as well. But yeah, I think fMRI is one cases that can use Swift for the research, and then maybe we have to find other applications that can use Swift for those data sets. Yeah, and Okay, I will accept the question from Jonathan first. So this multi-terminal is to avoid running. Oh yeah, so we experimented this model with A100 GPUs supported by the NERSC. So in the first slide, yeah, so we are cooperating with Brookhaven National Laboratories and the NERSC institution. So yeah, they support the A100 GPUs with multiple nodes. So yeah, maybe and the streaming. We did not stream the data sets, but yeah, trained as usual using A100 GPU. So for training the model with batch size 8, it requires about 18 gigabytes GPUs for the training. So I think it is affordable for most researchers who try to train this model with their computational resources. Yeah, but yeah, it totally multiple terabyte data set is very heavy. So yeah, I cannot run multiple times for those multi-terabyte data sets. So we split the data set and then test the model with the samples of data sets in most cases. Yeah. Okay. Would it be the answer for you? Is it enough? Okay.
Yeah, Teresa has her hand up. I think she has another question.
Yeah.
Yeah.
Okay.
Thank you.
Okay.
So I was wondering, so since we know from large-scale connectomic studies that both the structural and functional connectivity greatly differs across subjects, especially in the case of various neurological and psychiatric disorders, to what extent do you think that for all sorts of clinical research applications, further pre-training or denoising would be needed to make this model universally applicable and accurate and generalizable given the differences in connectivity?
Yeah, I think I agree with your opinion regarding the quality of data sets. So yeah, as you can imagine, this model can be very vulnerable to those kind of the noises or artifacts, such as head movement or kind of scanner effect as well. So if we want to transfer the pre-trained model to the other data set, considering those kind of points would be one of the biggest issues. So we are now trying to apply the pre-trained models on other data sets, such as ABI data set for autism spectrum disorder prediction. And then it did not show the higher performance as we expected. So we are finding the reason for this moderate performance in those kind of data sets. So it could be caused by the quality of data set, or it's maybe deficiency in the pre-training data sets. So yeah, I think we have to investigate those issues more. Yeah. Yep. Okay. Yeah, so regarding the patch size in Swin Transformer, we have tried it with different patch size digits, and we adopted patch size of 4 in this context, and so in most cases this patch size showed the highest performance, but depending on the data set, the patch size can determine the performance of the model. So it should be one of the major hyperparameters that can tune the model. And maybe you can find those results at the open review of our Swift grips open reviews for grips maybe. Okay. Yeah, thank you for your question. Okay. So please ask another question.
Okay, one last question. So I was wondering if you
Yeah,
think that given the inherent uncertainty and possible noise involved, it might be suitable to, after obtaining the transformer outputs, to deploy various Bayesian approaches or algorithms to basically obtain more accurate predictions. And if you think such a pipeline would be possible and
yeah.
possibly preferable.
Um, okay. Okay, can you ask that again? Yeah, I think I didn't understand your question clearly.
Yeah, so
Yeah,
again, in like
yeah,
more general, not necessarily visual processing domains, in the
yeah,
context of transformers, given
yeah,
that inherently their outputs are probability distributions,
yeah,
sometimes researchers try to like augment their pipelines by feeding the outputs of those
yeah,
transformers to like further algorithms that use a bunch of Bayesian techniques such as Bayesian risk
yeah,
and
yeah.
whatnot to basically try to achieve higher accuracy. I don't know how widespread of a technique this is, but I read about it a bit and I was curious if you think
Yeah, yeah.
such a thing might be needed and useful.
Mm. Yeah, I think one of the feasible approach for this kind of models. So yeah, compared to large language models, those kind of research is very it did not uh, nobody explores these kind of models for applying the Bayesian models or analyzing the layers for the model. So I think those kind of approach can further increase the performance of the model. And not I have not tried those approaches. Yeah, so I don't have much insights regarding your questions, but I think it might be a feasible approach that can make it better. Yeah,
I guess related to that,
yeah,
I think any sort of, cutting edge approach being used without using like the outputs of a pre-trained model would probably be worthwhile, right? Like my
yeah,
understanding is that a foundation model basically gives you potentially better inputs
yeah,
into whatever the standard pipeline is for any sort of task that would be in the fMRI realm. So like if Bayesian risk or whatever is working well for a certain task, probably would also work well with this, right?
yeah, yeah. I think so. Yep. And Jonathan have another question. So I'm serious to simplify it.
Does your model have
Oh,
a training data
yeah,
bias between different modalities? Like I understand you're training on a couple different types of data here, but for a lot of the models I'm familiar with, they're trained primarily on vision data or images, things like that. So does this model have a preference for modality like that, or are we just simply trying to map fMRI space with this pre-trained model?
yeah. So I've tried this model for training the fMRI dataset only, yeah, but um, maybe it has some. Yeah, so yeah, I didn't think much about those questions, so sorry to say that. Yeah, I'm not sure how to answer to the question. Yeah, so yeah,
It'd be
yeah,
interesting
so
to see what kind of performance dynamics it has across brain areas, because if you're
yeah,
training primarily on data from specific types of tasks, then
yeah,
perhaps there's a little bit more neural variance in specific regions of the brain that might be more attuned to the tasks that the data you were training on was using. So that was the
yeah.
reason I asked.
Mm, yeah, I think. Mm, yeah, I hard time figure out the issues. So yeah, mm, yeah, okay. I'll just think over about your question a little bit. Yeah. Okay. Mm, yeah. can I firstly hop into another question to answer? Yeah. Okay, so ensure times reduce initial prep. Oh yes, so in those cases, if you want to use the pre-trained model, then we have to zero pad to make it fit for the data set. But in most cases, we can just use the shorter model. Yeah. So if you want to train the model from scratch, then you can just decrease the sequence length for the data set. Then the model size will decrease to accommodate the data set. But yeah, if you want to use the pre-trained model, then I recommend you to simply zero pad the data set to fit on the model. Yeah. Yeah.
A question about the losses. So
Yeah.
you do two different contrastive losses, right?
Yeah.
What is why only use contrastive losses? Is there room for, directly trying to like predict what was the fMRI input from the model? Like, why did you settle on specifically using contrastive loss and specifically these two kinds?
Oh yeah. So the reason why I used contrast loss is to make it capture so make the model to capture the individual difference between subjects and learn the local and global dependencies between the fMRI volumes. But as you ask, in most transformer models, we adopt the masking loss. Yeah, so maybe a kind of mask image modeling, kind of those approaches very popular nowadays. So I think it is a feasible approach for pre-training the model with Swift as well. But so the formation region was the reason why we used the contrast loss. But I think using other pre-training strategies would make it more better for training the fMRI data as well. Yeah, so
specifically, the model, in other words, is being trained specifically to be able to figure out, given many samples, like whether a sample is from like the correct original subject versus someone else's sample. Like that's one of the losses. And then the other loss is like assuming that all the samples are from the correct subject, is the given sample the original sample versus like one in the future or in the past? Is that correct?
Yes, is definitely is correct. Yeah. I think it's the pre-training approach is the preliminary result with the Swift. And I think so we are preparing for developing the better pre-training strategies for using Swift for foundation model. So I admit that it is not enough to make a foundation model with these losses because this contrast loss is not popular in this kind of image modeling. So maybe we can try another approach for pre-training. And so we are developing on those kind of strategies as well. Okay,
Yeah, I'd
so
be curious if because the performances that you report are like age, sex, intelligence. I'm really curious about how well it works on task-based decoding, or for, you know what I mean? Like other than just the person's identity of like whether like what's the person's age or sex or intelligence, like the foundation models are ultimately useful when they're very versatile in the downstream applications, right? And these losses are not going to tell you like specific information about like the patterns of voxels in specific regions, probably because the loss isn't designed to learn that information.
Yeah, it is. So I think there are some limitations using these pre-training losses. Yeah, like for the issues like you mentioned, and yeah, applying this model for task fMRI is one of the biggest things to do in the near future. So we are testing this model for predicting the reaction time in n-back tasks. So it is showing preliminary results regarding those experiments. And maybe we can show the results in the near future regarding your questions. And I think, yeah, everyone try to use task fMRI can evaluate their performance with Swift as well. Yeah. Okay, so Jonathan has another question. So that's between oh, there's a different things. Yeah. So I got your point. So yeah, we implemented it to make them. Yeah. So I understand your question. So yeah, if we make it just randomly, making the contrast loss to input the data set, then we cannot consider cases that the fMRI scans are overlapping. So we implemented it to exclude those cases when the fMRI sequences are overlapping. Yeah, so yep, so it is not perfectly random because we implemented it to make it distant in contrast loss. Yep. And do you have any questions?
Definitely feel free to ask more questions because
Yeah.
I can always ask questions.
Yeah.
So I didn't understand how you do interpretation maps. Can you go into more depth for that?
Yeah. Okay. Thank. Yeah. So regarding the interpretation map, we acquired the interpretation map with so we have subsequences for the fMRI input. So so for the sixth input, so we can, if you use integrated gradients, we can acquire the interpretation map for the input data. So
yeah, what is an integrated gradient?
So it is the interpretation method for the deep learning model. So it's hard to explain the exact algorithms for integrated gradients, but it is a famous approach that so it is comparing the cases. So it mixes random noises to the data set and then compare. So so measuring the impact of the noises in the input data. So by mixing the noise, then we check the most important regions that have higher impact on the final results. So yeah, this map means the comparative impact of each input voxels to the output. Yeah, is it enough for your question?
So So it's kind of like you have your finished model, and then you can you can try feeding in noise in a certain way, I guess, to see how the network handles it. Am I following correctly?
It's almost correct. Yeah, so kind of mixing noises, then finding the exact find the major regions that has a more consistent effect on the final results.
So if you're specifically interested in sex classification, for instance, then so the sex classification, this is something that's like a decoder to classify sex that you append to the end of the Swift model, the pre-trained model, right? So then in doing this sex classification task, you go through the go through the pre-trained model, which then goes through the sex classification. And what you're saying is that you can repeat that process with different random noise and see where the neural network is most consistently working to give you the final output. And then that should be where I guess, that tells you what's the most informative parts.
Yes, it is. Definitely. Yeah. Thank you for,
So then how do you then map that onto the brain map like this with the heat map?
So so we can map those impacts on the input data set. So it is just final results. So so what is your exact question?
So like if you have a neural network, right, of transformers or whatever, then being able to see the weights and biases that are most important doesn't mean that you can then immediately project it onto the original 3D volume of the brain, right? So how do you take like consistent weights and biases of the later layers and then undo it to project it on the brain?
So it is provided by the integrated gradient modules. So it considers the weight and biases to run this model, but the final results of the integrated gradients is the same as the original input data. So we can express those heat maps for the input data.
Okay, thank you for explaining that. That seems like a really useful approach. I
think it's really a useful approach. And do you have any question, Scotty? I think you have a lot of questions.
I have plenty of questions. I just pause in case other people have questions. How does Swift handle long-term dependencies of like, the Swift and Swin in general, it has like the hierarchical window approach. But does that mean that there's a trade-off in the sense that if you have, 10 seconds in the future in a different part of the brain, like frontal lobe versus occipital lobe, if there's some important pattern between the two, like is Swift worse when it comes to that compared to a normal transformer?
So I get your point. We implemented Swift for accommodating all the ranges for about in the time dimension, it can afford about 20 to 30 volumes, and that it can cover those lengths, and then it can cover the all 3D volumes in the finer layers. So if we input the 96 voxels, 96 by 96 by 96 volumes with our basic Swift model, then you can accommodate all the ranges in the volumes. So I think, the Swift is enough to consider the interaction between the frontal lobe and visual cortex.
But even if it's possible for at some point the model can integrate the information from one part of the brain to another, it's at a later stage in the transformer hierarchy of like the multiple stages that you have. And so presumably there's a bit less, it's a bit more impoverished at the point later in the model when it does handle the ability to be within the same window, right?
Yeah. So for those reasons, we built the global rotation block at the last layer to aggregate all the attention over the patches. So I think as you mentioned, if we just adopt this shifted window layers, then we can lose the long-term dependencies between the brain regions. But by applying the global attention layers at the last layer, then we can cover all the regions at one point. But as you mentioned, we can custom it to make it more global attention layers. But it might take more GPU resources to train those models. So it depends on the task and problems that you want to target.
I see. Thank you.
Yeah.
Another kind of finicky question is about positional embeddings.
Yep.
So you talk in the paper about how you found that absolute positional embeddings outperformed relative, if I'm understanding correctly. Why is that? Why do you think the absolute worked better?
Oh, I think it's in fact it is the research from so the biggest reason for using the relative position encoding is that the previous model that uses Swin Transformer called I'm not sure you have heard the model Video Swin Transformer has applied the absolute position embeddings to make them accommodate the temporal dependencies. So we tried the absolute position embedding for this approach, and then it worked better, as well as it was more efficient. So it's hard to explain the reasons for the better performance. So I think,
because I don't really understand. I mean, maybe if all the brains are aligned perfectly, then it kind of makes sense that absolute would work better than relative. But you know, brains are always like shifting a bit, and you're even going across data sets in different subjects. And so I don't know, my hunch would have been that relative maybe does better, but that's clearly not the case. And I don't really understand the intuition of why absolute works better.
Maybe the reason for that is because we applied registration for the fMRI dataset, so it was aligned to the same space. So I think the reason why the absolute position embedding works better would be the way we process the dataset as well.
Because they're all in a template brain that's the same?
Yes, it is.
That's the reason why?
It can be. Oh yeah, I'm not sure. I cannot assure that it is the reasons, but I think it can be one of the reasons.
Interesting.
Yeah.
Also another quick question is you had a slide that said 100,000 subjects equals 120 terabytes. Do you have 100,000 subjects?
Oh yeah, I think it's a great question. So we now have about for about 40,000 subjects in the separate storage. We cannot save all the data set at one storage. So we are transferring the data set from one space to one space to the other space. So,
where are these 100,000 subjects coming from? Because I thought UK Biobank only has 10,000.
Yeah, 10,000. Oh no, not 10,000. They have 40,000 data sets.
40,000.
Yeah, 40,000 is open, and if we include the task fMRI data set, it can be more. And so it is just for it does not mean that I have 10,000 data sets for now, but we imagine that we can collect those those amount of data set if we can aggregate the resting state and tasks fMRI from UK Biobank dataset. and if you include the resting and task dataset from ABCD dataset, it amounts to 20,000 data. And maybe we can also include the HTTP dataset or any other kinds of similar dataset. Then I expect that it amounts to not exactly the 10,000, but maybe close to those amounts, I think.
You mean 100,000?
Yeah, 100,000. Yeah.
So UK Biobank has over 40,000 subjects?
Yeah.
That's a lot.
Yeah.
So that's about how many that you pre-train the model on.
Yeah. But I didn't write the exact numbers in these slides, but we only trained the model with about 10,000 samples. So I think it's really a preliminary result for our approach. Yeah. So to train the model with those kind of for the whole data set from UK Biobank, it requires much more resources. So we are short of the resource for now. Yeah. So we are making it more efficient we are optimizing the model architecture to accommodate those kind of models. So as you might know, there are so many techniques by NVIDIA to making it model more lighter and increasing the memory capacity for the model.
Last question by me. What was the slide that had NeuroX? Is that just what you're calling all of the data sets? I think I just missed that part.
Yeah. So NeuroX is just in fact, this name is from my principal investigator, Jiuk Cha. So he called this project making the foundation model for fMRI or EEG dataset as NeuroX. So maybe it means the possibility of neuroimaging dataset for further application. So so he named it as X. So it has a lot of potential for the future research. Yeah.
All right, cool. Yeah, cool name.
Yeah. But we haven't opened this name yet because as you see in the sheet paper, we did not emphasize the model's role as foundation model. So it is just for presentation because as I know, all of you are interested in the foundation model. So I proposed it as a potential approach for foundation model. And I think it is not perfect for now. So so from your advice or questions, I was highly impressed that there are so many issues I have to target using this model for foundation model. And I think we can prepare, or maybe we can cooperate each other to make it better.
Yeah, no, I'd love to collaborate. Just so for reference of what we're kind of working on right now is that we are adopting the video MAE model basically to do like masked autoencoder for 4D brain volumes. So we're not doing like this same kind of contrastive approach. We're doing what you mentioned before, basically, of the masking. And right now we're training basically across open neuro. So, but another important difference is that we're not doing the full pre-processing chain. We're hoping that the model can learn how to do the pre-processing. So that's like the big difference here is you do fMRI prep, all the standard pre-processing steps, and you normalize to a shared brain template. That assumedly would lose some data, some signal from the data.
I think so.
Not necessarily the pre-processing, but I mean normalization in general. When you deform a brain or you move it to a new space, you lose some signal. And the model is relying on having a template brain that is shared across all of the samples, which is going to make performance worse if
Yeah, I
you are
think
not
so.
in that template brain.
Yeah.
It's I mean, ideally, you would want the model to be able to learn generalizable across
Mm-mm.
different, different brains, different machines, different tasks, have different downstream performance evaluation metrics. And
Yeah.
maybe it's optimistic for us to think that the model can learn how to do basically pre-processing steps and be able to handle brains of different sizes and shapes. That's kind of still something we'll have to see if it works or not.
Yeah.
But
Also,
yeah,
yeah. So do you trying to do those things for the fMRI model or any other approach? So have you ever tried those approach with your model or any other approach for that?
or what model?
Yeah. So I'm asking you whether you already are trying to use your own model for pre-training the
Yeah,
those kind of data sets,
yeah,
right?
we're currently doing the pre-training of
Yeah.
the basic adapting like video MAE approach.
Yeah. It's really
Yeah.
interesting.
So like, taking the brains, patchifying them, trying
Yeah.
to recover the voxel patterns
Yeah.
in the raw volumes
Mm-mm.
that,
Yeah.
that get patched. So
Yeah. How much samples in open neuro data set?
that's a really interesting question
Yeah.
because
Yeah. There are
I
so
was
many.
trying to
Yeah.
find there. I
Yeah.
can't find the information
Yeah.
for that, but I
Yeah.
am currently scraping. I'm currently going through OpenNeuro and like
Yeah.
pulling the data out,
Yeah.
and like it's you can't really find the information online on the OpenNeuro website of how much
Yeah.
subjects. There
Yeah.
are 1,012 data sets that are
Yeah.
fMRI, I
Yeah.
believe.
Yeah.
And right now it's currently running. The model is currently
Yeah.
running, and we're like 7% through because I started running it like this week. But
Yeah.
based on just 7% of all the possible data sets, it's like 1,800 subjects.
Yeah.
So it should extrapolate to maybe like 20,000 subjects or something. And but I mean, it could just be that. I mean,
Yeah.
don't hold me to that. I don't know
Yeah.
the exact number,
Yeah.
but
So,
presumably a lot.
yeah.
Maybe on the scale of UK Biobank.
Mm, yeah. I'm curious.
Probably less,
Yeah.
honestly.
Yeah.
Probably a bit
Yeah.
less than UK Biobank.
Mm. Yeah. I'm curious whether there isn't any issues regarding using the raw data set because, yeah, as
Also,
the
the data
other,
quality is assuredly
yeah.
much better for UK Biobank than OpenNeuro because it's like
Mm,
all different data, all different machines, not really standardized.
yeah, I think so.
Some of the data
Yeah.
sets are not even whole brain. It's like you could get half of a brain.
Really? Oh my God. Yeah. Yeah. I hope it works. Yeah.
But yeah, if you're
Yeah.
interested in collaborations, we can definitely talk outside of this meeting.
Yeah, I think so. Yeah. I was so surprised that somebody else in the world are trying the similar approaches my laboratories. So I think it's a great starting point for our collaboration.
Yeah, definitely. And I mean, you were able to, release your model and everything. So
Yeah.
it's possible to adapt a Swin-based approach to masked autoencoders, I think.
Yeah,
So
I think so. Yeah.
that would be the obvious kind of collaboration point.
Yeah, I think so. We were thinking about using Swift for mask image modeling as well. So yeah, maybe we are in the similar stage in this research.
Yeah. Our side, we're very early on. So
Yeah.
yeah, we don't have any results or anything. We haven't even gotten the training pipeline to fully be operational yet. It's just, in the progress of getting to a working state. Like the training loss goes down, but like all the things about implementation still need to get figured out.
Yeah. Mm.
anyway, yeah, we can talk more about this outside the meeting, but thanks everybody so much for attending this reading group, and Junbom for presenting your really cool work. Let's give a round of virtual applause. And yeah, thanks so much.
Yeah, thank you so much for listening to my presentation. Yeah, and I was really impressed by your insights in this kind of research. Yeah, so thank you for your attention.
Thank
Take care,
you.
everyone.